In this lesson, we will learn about segment relationships in circles by answering the essential question, how can we estimate the distance to the horizon using results about segments related to circles? So, a secant is a line that intersects a circle in 2 points. So notice that this line J intersects this circle in exactly 2 points. Therefore, we call line J a secant. Contrast that with a tangent line. A tangent is a line in the plane of a circle that intersects the circle in exactly one place. You may ask, why do we in the definition, why do we mention that the tangent line has to be in the plane of the circle and that it intersects the circle in exactly one point? Well, the reason is because you can have a line that is not in the plane of the circle. Imagine this line basically coming straight at us and still have it intersect in exactly one point. Okay, so we need to specify when we're saying that when we're talking about a tangent line, the line that we're talking about has to be in the plane of the circle. A secant line, notice we don't say that at all. The reason is because the only way for a line to intersect the circle in 2 points is for it to be in the plane of the circle. There's no way for a line to not be in the plane of a circle, but at the same time intersect the circle in 2 points. It's impossible. So, if a secant and a tangent intersect in the exterior of a circle here, then the product of the lengths of the secant segment, AC, and its external segment, BC, equals the length of the tangent segment squared. Okay, so basically you take the entire length of this secant segment here, multiply that by the external secant segment, BC, and what's interesting is when you have that product, it's always going to be equal to the square of the tangent segment here. But why is this happening? Well, the reason why this is happening is because essentially what we have here are two similar triangles. So if we draw in line segment AD and BD so that we make two triangles, the big triangle CAD and CDB, it turns out that the big triangle CAD is similar to the triangle CDB. We're going to prove that now. And from that, the fact that those two triangles are similar, comes our secant-tangent product theorem, which is the theorem that I just told you here, this equation. So, from a result we learned previously, if we take a look at the measure of angle CDB, it's always going to be half the measure of the intercepted arc. Well, the intercepted arc here is BD, arc BD. Okay, so what we get is the measure of arc of angle CDB is exactly half of the measure of this arc, whatever it is. Also remember that the measure of angle CAD, so this angle here, is also equal to half of the intercepted arc by the inscribed angle theorem, because this is an inscribed angle. Okay, so both of these angles, this angle here and this angle here, touch the exact same arc of the circle, which means that they have to be congruent angles, okay, by the substitution property of equality. Also, notice that, of course, this angle C, is congruent to itself. Okay, so if you think about this, now we have two triangles that share two angles. Okay, take a look at this big triangle CAD and the small triangle CBD. Notice that they both have one congruent angle, but in fact they both actually share a common angle in angle C here. Okay. So by the reflexive property of congruence, angle ACD, which is this angle, is congruent to angle DCB from the smaller triangle, this one. Now, since these two triangles have two angles in common, I know that those two triangles have to be similar. So using the angle-angle similarity postulate and basically taking these two triangles, separating them from the circle so it's easier to see, I know that triangle CAD is congruent to triangle CDB. Since the corresponding sides of similar triangles are proportional, I know that AC is to DC, so AC is to DC, the same way DC is to BC. By cross multiplication, I get the secant-tangent product theorem, which I was trying to prove, and here it is. Alright, so now we're going to see an application of the secant-tangent theorem. Okay. By solving a problem involving approximating the distance to the horizon of an observer above the surface of the Earth. So let's say I have an observer that's 0.1 kilometers above the surface of the Earth here at point C. The radius of the Earth R is given to us at about 6,000 kilometers. So I know this distance R. We need to calculate, just based on the radius of the Earth and how far this observer is above the surface of the Earth, we can find the distance to the horizon. So the secant-tangent product theorem tells us that the length of the secant segment, or the product of the secant segment times the external secant segment, so this segment here, BC, is equal to the tangent segment squared, which just says that AC, the secant segment here, AC times the external secant segment BC is equal to the square of the tangent segment, so that'd be DC squared. So if we put this in terms of the radius of the Earth and the height of the observer, notice that AC, the length AC, is just R plus H, or we can also write that as 2R plus H. So AC is the same as 2R plus H, where BC is just the height of the observer above the surface of the Earth, so I can use the symbol H to denote that. And D, the distance we're trying to find to the horizon, I just denote by D. So DC, I'm just calling distance to the horizon D. Okay. Now, I know they're giving us in the problem the radius of the Earth. We know what the radius of the Earth is, and we also know what the height of the observer above the surface of the Earth is. What we're trying to find is the distance to the horizon, from the observer to the horizon. So basically what I need to do is solve for this variable D. And in order to do that, I just take the square root of both sides, and I get that D is equal to the square root of this expression. But I know the value of R, it's the radius of the Earth. I know the value of H, it's the height of the observer above the ground. So I just substitute those values into my expression for D, and I get that the distance to the horizon is approximately 35.7 kilometers. Alright, so the essential question that we addressed in this lesson is, how can we estimate the distance to the horizon using results about segments related to the circles? Well, all you have to do is apply the secant-tangent product theorem to find a formula for the distance to the horizon and then use it to solve the particular problem that you're looking at.